Okay, 7.1 is rational functions, and in all reality, the next couple of sections are going to be rational functions. So this is more of a introduction and how we can cancel things. So let's get into it. This one's going to be a little bit long. So a rational function is generally a fraction that has an x on the bottom or an x on the top or x's in both spots. That's kind of the simple definition of what it is. And so when we're dealing with rational functions, there are certain values of x that make it so that we can't either graph it at that point or we can't evaluate it at that point. And so we talk about that being out of our domain. So domain really is what are the possible values for our function that do work. But generally the best way to kind of think about those or approach those from at least the start is to think about what values x can't be. And so if we have a nice rational function where we have nothing in the denominator, we can just go ahead and dive in and say the domain is all real numbers, or if you want to do interval notation, parentheses negative infinity to infinity, close parentheses. I'm fine with either. Yeah. But if we have an x in our denominator, we have to be a little bit careful because we're not allowed to, in mathematics, divide by zero. Dividing by zero is so complicated that even the smartest mathematicians tend to say, oh, it's undefined, I don't want to worry about it. And so we have to consider that. And when we have a rational function, we want to avoid dividing by zero. And so even though the domain is everything that x can be, we kind of talk about it in an opposite. We find what x can't be, and then talk about how x can be everything but that. And so we find those values that x can't be by setting the denominator equal to zero and solving. And so sometimes if you wrote or you were writing up your work and just wrote x minus 8 is equal to 0, that's fine. But technically we are trying to avoid that happening. So I kind of put a dash between the zeros. And so then we would add 8 to both sides. And so x can't be 8. But that's not domain. Domain is everything x can be. And so we would talk about everything less than 8, which would be negative infinity up to 8, and everything bigger than 8, which would be 8 to infinity. And that's my domain. So this next problem is a little bit more complicated, but the concept's the same. For starters, I want to figure out what would make my denominator equal to 0. And so I'm going to set my denominator equal to 0 and then solve. And so this is an equation that we can factor. If I look at -2 times -4, that gets me 8. And if I add those two, I get -6. And so my two factors are x minus 4 and x minus 2. And now I set each equal to 0 and solve. So x can't be 4 and x can't be positive 2. Now this interval notation becomes a little bit tricky, but we've seen interval notation before. And that concept is I talk about my smallest value, and then it's kind of reading a book that when I'm telling my story, I go from smallest value to next smallest value to next smallest value all the way up to my biggest possible value. And so all of the values less than 2 are good. So my first parentheses, or the first piece of my domain, is going to be negative infinity up to 2. And then I'm also going to have 4 to infinity, everything bigger than 4. But what I just was missing in that kind of explanation of my domain is I can have stuff between 2 and 4 as well. And so when you see these situations where you have two things missing in your domain, you're going to notice that you're going to have things that look like this a lot. Because I need to include everything less than 2, I need to include everything between 2 and 4, and then everything greater than 4. Now, one of the simplest rational functions, and I guess it's technically not a function because it doesn't have an x or some sort of input, but it's just a generic fraction. And so if we recall how to simplify those fractions, generally what we did, and maybe if you got good at doing the simplifying fractions, you were able to kind of skip this step. But realistically, what you were doing was you were pulling out the greatest common factor from the top and then from the bottom. So yes, when you have 6 divided by 8, people tend to think, oh, I divide the top by 2 and the bottom by 2. But really what you're doing is you're factoring out a 2 and then canceling that and that leaves you with 3/4. So yeah, that's a bit persnickety and precise when we're talking about simplifying, but that's going to build into a more important concept. So now this is the more complicated example. So now I have a rational function. I have something on top that I can factor. I have something on bottom that I can factor. And in fact, the bottom is one of the special factoring difference of squares. So I get x plus 3, x minus 3 on the bottom. And the top I'm not really technically factoring. X plus 3 squared is just x plus 3 times x plus 3. But with that, if I have matching factors and they have to match completely, the signs have to match, the variables have to match, the numbers have to match. But if that happens, I can cancel out those specific factors and simplify my rational function. And sometimes I can simplify them very drastically to the point that I would actually have a simple fraction once I'm done with the whole process. And so that's the kind of the idea for the next couple of slides. Here I have 3x squared over 9x cubed minus 6x squared. Can't really factor the top, but I can pull a GCF out of my factors on the bottom. In fact, I can pull out a 3x squared. So that leaves me behind 3x minus 2. And now, even though they aren't really seem like factors because they don't have a parentheses and two terms, I do have 3x squared on top. I have 3x squared on the bottom. I can cancel it. Now, a big error that I see in this, and this is an error that I mention a lot when we're doing factoring, is when we think of canceling, we think of 0. And that's not true when we're dividing or multiplying. When we are dividing or multiplying and terms cancel, we are left with 1. And so I have 1 on the top, 3x minus 2 on the bottom. So now, when we start to get into more and more difficult problems, organization starts to become very important. So in this case, I have a problem where I'm going to have to do factor by grouping twice. And so for this slide, I'm going to use different colors. But if you're doing it on a piece of paper with a pencil, I would maybe just rewrite both of them in almost very separate spots and then keep track and say, this is the top, or this is my numerator, and this other one is my denominator or the bottom. And so with factor by grouping, I do 6 times 12 gets me 72, 17 on the bottom. I want to find two terms that add to get me 17, multiply to get me 72. Those two things are 9 and 8. And then I break things up. 6x squared plus 8x plus 9x plus 12. My GCF in the first thing is 2x. Leaving me behind 3x plus 4. My GCF in the last two terms is 3, leaving me behind 3x plus 4. And so my two factors are 2x plus 3, and then 3x plus 4. Let's breathe for a second. And then now we move into the denominator. So factor by grouping again, 2 times 3 is 6. And then I want to add to my middle term, and so those two things are 2 and 3. So I rewrite my problem as 2x squared plus 2x plus 3x plus 3. And my GCF in my first term is 2x, leaving me behind x plus 1. My GCF in my last two terms is 3x plus 3, or sorry, it's 3, leaving me behind x plus 1. And so my factors for that are 2x plus 3 and x plus 1. And now I can rewrite my rational function as 2x plus 3 times 3x plus 4 on the top, and that's why I kind of used color coding, and then 2x plus 3 times x plus 1 on the bottom, and then I can cancel my 2x plus 3's, leaving me behind 3x plus 4 over x plus 1. Now, sometimes it seems like I can't actually cancel things, and this is very similar to a concept we had with factor by grouping. You'll see why shortly. But here I have things that are close, but they're not exactly the same. One of them has a minus x, one of them has a positive 1, and one of them has a minus 1. And so I don't actually have the exact matching happening here. But I can pull something out or factor something to make it so that my sides flip. And that thing is that wonderful, magical -1. So here I probably should have written a -1 on the top, but I just pulled out a negative. It's fine, they're equivalent. They kind of have that invisible -1. And so then now they do actually match up. Not the signs aren't on the wrong variables or the constants or whatever. And so I can cancel those guys and I'm left with -1/1, which is actually just -1. And so this is a case that I talked about a couple slides ago, that sometimes when we simplify our rational functions, we get a really nice answer that, depending on the context of a word problem or an application problem, will make our lives very easy. Now, multiplying fractions is almost exactly the same that we've done before with simplifying in the last couple of slides, because when we multiply fractions, we just multiply straight across. And so although it seems like we have two separate fractions happening, we can almost treat it as though it's just one giant fraction with 15x squared on the top, 15x squared times x cubed plus 1 on the top, and -5x minus 5 times x squared minus x plus 1 on the bottom. And now I just treat it as a really big fraction. I'm just going to kind of factor each piece. So the top left is actually a special factoring, factoring a sum of cubes. The top right can't be factored. The bottom right actually can be factored. You can try if you want to, but there's no two things that multiply to get you 1 and add to get you -1. And then the bottom left one factors with a GCF. I can pull out a -5 out of both terms, and I'll be left with -5x plus 1. So really the only thing that I'm going to factor is the top left. And just using my formula, my a is going to be x, my b is going to be 1. So then I fill out my formula, I get x plus 1 times x squared minus x plus 1. And now I'm going to go through and cancel. I'm going to cancel things that are on opposite sides of the fraction. If they're on the same side of the fraction, I can't cancel that. So the things that match up are x plus 1 on the top, x plus 1 on the bottom, x squared minus x plus 1 on the top, and that's on the bottom too, even though they're on separate fractions. Like I mentioned, just kind of treat it as though it's one giant fraction right now. So they're on opposite sides of that bar, one's in the numerator, one's in the denominator, and so we can cancel. And then the last thing we can cancel is more of kind of a reduction. So I'm left with just the 15x squared over -5. Oh, 15 divided by -5 gets me -3. So -3x squared. Now, this is certainly the most complicated question you're going to see when we're simplifying rational functions, for the reason that we are going to have to factor 4 different times. And what's different about this question versus the last question, other than it's a very big question, is now we're dividing. And so if you're dividing fractions, you have to do that initial step whenever you divide fractions is you're going to leave the first fraction alone. You're going to flip the second fraction and turn it into a multiplication problem. Ooh, maybe I'm going to do that later. So spoiler alert, I'm going to do that later. Instead, I'm going to focus on the factoring. So again, I'm using color coding. That's what I recommend to organize things, but you might not have fancy colored pens. So just make sure that, like, I would maybe number it or put letters next to it to keep track of where things belong, so that when you put things back together, you put them in the correct spot. So the first thing I'm going to factor is 10x squared plus 23x minus 5. So now we've done factor by grouping about 20 times at this point. So I'm going to go through each of these fairly quickly. Just go ahead and pause if you need to take time to write things down. So factor by grouping, 10 times -5 gets me -50. I just bring the center term, the one next to, or the coefficient of x, as 23. And now I want two things that multiply to get me -50 and add to get me 24. And so those two numbers are going to be 25 and -2. So I split up my 23x term into 25x minus 2x, and then I get my two separate groups. My first two terms have a 5x in common, and so I would be left with 2x plus 5. And so my second two terms have that kind of trick of I can't really pull out anything more than a 1, but if I only pull out a 1, my signs are not going to match up. So I'm going to pull a -1 out of both of those terms, leaving me with 5x times 2x plus 5 minus 1 times 2x plus 5. And so my two factors are going to be 5x minus 1 in front of the matching factors, and then 2x plus 5. And that's my first thing that I'm going to have to do factor by grouping for. Now I'm going to factor the bottom of the left fraction, 5x squared minus 51x plus 10. Factor by grouping. The order is really off on this, but that's fine. Oh, wow, really off. So I want to, 5 times 10 gets me 50, and then the middle term is -51. So I want two things that multiply to get me 50, add to get me -51. That's -50 and -1. And so I break up my middle term, leaving me with two groups, 5x squared minus 50x minus x plus 10. My GCF in my first two terms is 5x, leaving me with x minus 10. I'm going to pull out that -1, so I have x minus 10 left. And then my two factors are 5x minus 1 times x minus 10. Hopefully that's the only wrong animation that I have, but this slide has, I think, 50 animations, so I can't promise that. Now on to factoring the top right, 2x squared plus 9x plus 10. You guessed it, we're going to do factor by grouping, and also my animations are off. So I want to find two things that multiply to get, or I multiply my 2 times my 10, I get 20. I bring down my coefficient of my x, I get 9. I want two things that multiply to get me 20, add to get me 9, those are 5 and 4. I break things into my two groups, 5x or 2x squared plus 5x times 4x plus 10. I pull out an x out of my first two terms, I pull out a 2 out of my last two terms, and so I'm left with my final factored form, x plus 2 times 2x plus 5. And I get to factor again. I'm factoring the bottom right, 7x squared minus 68x minus 20. I'm going to do factor by grouping. Do 7 times -20 gets me -140. My coefficient of x is -68. I want two things that multiply to get me -140 and to get me -68. Those two things are -70 times 2. I break things up. I get 7x squared minus 70x plus 2x minus 20. And then I can pull out a 7x out of my first two terms. I can pull out a 2 out of my last two terms. And so my final factored forms gets me 7x plus 2 times x minus 10. And so if I put everything back where it belongs, that's why I kind of did the color coding, my fraction becomes, or my problem becomes that top thing that I just revealed on the PowerPoint. And so now, if we're dividing fractions, what I do is I leave my first fraction alone, I flip my second fraction, and then I multiply. So now it becomes almost the exact same thing as my last slide, albeit more complicated. So now we can kind of just treat it as one giant fraction. I'm going to try and cancel things. There's a lot of things I can cancel. 5x minus 1 matches up. 2x plus 5 matches up. X minus 10 matches up, and so all of this giant headache, I am left with 7x plus 2 over x plus 2. And I would feel a little bit bad about the animations. I would feel a little bit bad about the pace of this slide, but this is not going to show up on the exam. And there might be one MyMathLab question involving this, but that's going to be it, and I'm sure the example will walk you through how to do this. So all of that's the reason why I feel confident saying that this will not be on the exam, and this is actually kind of an important concept to think about in any math class, is that when you have an exam, you have, in our course, I believe we'll have about 2 hours, maybe 2 hours and some change. This problem itself, sprinting through, I think I was able to get it done in 10 or 15 minutes, but I've done it before. I know all the tricks. I know how to factor it. I know all the little teensy things that multiply to this and that. So if this problem was on a test and I was doing it, you could probably double the time for me to complete it. And so that would mean it's 40 minutes, which means we can't really ask you that many more questions. And so when you're kind of working through problems, if you realize that even if you're like, I mean, maybe this is once you get the concept, but if you completely get a concept and you're taking a half an hour to get the problem done, it can't be asked on a test unless it's a weird test with 4 questions, which we won't see in this course. So that's why I don't feel like I need to slow down this one or re-record this one with the animations paying off, is because this is probably, if it's not the second to last time, or it's going to be the last time that you see this problem of this difficulty.